Hello everyone, welcome to the session on VM-friendly networking on Kubernetes. How many of you are familiar with Kubernetes? Hopefully a lot of you. Yeah, that makes it easier. So this is the open source summit, not the Kubernetes summit obviously, so I just want to share with everybody what Kubernetes is. And I'm very happy and grateful to be here at the Open Source Summit and to get an opportunity to be present in front of you. So let's get started. I'm going to be talking about VM-friendly networking on Kubernetes for the next 30 minutes. I'll talk about how you can create customizable networks. I'll also show you a live demo on how you can do seamless live migration for your VMs on Kubernetes. And hopefully you will walk away from the talk with some best practices on deploying VM workloads on Kubernetes. A little introduction about myself. I'm Surya. I'm an engineer working at Red Hat on OpenShift networking. OpenShift is the productized version of Kubernetes in Red Hat. I'm also a contributor to the special interest group networking in Kubernetes upstream. I'm also an OVN-Kubernetes maintainer. You'll be hearing a lot of the OVN-Kubernetes project here during my talk. And this is one of the network plugins that helps you get networking for your workloads in Kubernetes. And let's get started with the talk. So a brief introduction into Kubernetes networking model, just to context switch into this talk. In Kubernetes, the smallest deployable workload unit is a pod, obviously. And inside a pod, you can have one or more containers. Kubernetes networking model assumes that all pods can talk to all pods on your cluster. So there is this one cluster-wide pod network. This is what spans your cluster, which is enabling networking between your workloads. It's an open communication model, so every pod is assumed to be able to talk to every other pod in your cluster, and every pod usually gets a unique IP address, and no two pods can have the same IP address. So these are sort of the basic fundamentals of Kubernetes networking model that Kubernetes assumes. In Kubernetes itself, an orchestration system that helps you deploy, scale, manage your workloads. At the end of the day, it's a bunch of APIs when it comes to networking. So Kubernetes itself doesn't implement the network platform for you. You need network plugins, right? That's where CNIs like OVN-Kubernetes, Cilium, Calico, and I'm sure there's various other CNIs out there in the CNCF and Linux Foundation ecosystem that help you achieve that overlay networking for your pods. East-west communication here for terminology is pod-to-pod networking on your cluster. So using this cluster-wide pod network, you're able to let your pods talk to each other. What does this cluster-wide pod network look like? That's up to each network plugin.
It could be an overlay layer 3 network, it could be an overlay layer 2, it could be a bridge network, or it could even be an underlay network. But we just assume that all pods should be able to talk to all pods. That's the basic for all networking on a Kubernetes cluster. And if you want your workloads to be available to external clients who are sitting outside the cluster, you almost always need to expose these workloads, that is your pods, using services or using gateways or ingress. So using the service API or ingress or gateways, that's what gives you a gateway in to be able to reach your workloads, because all your pods are protected by default and they can only be reachable within your cluster. So these are some of the fundamentals of Kubernetes networking model, which will hopefully set path for the rest of my talk. And the egress and ingress that I mentioned here, the NATed model, is what is also called the north-south communication. So your pod IP is never exposed to external clients outside the cluster. This is almost always a NATed structure, right? So the packet leaving your cluster is always so snatted to your node IP. Network security. So given that the communication of pods in your cluster is always open, all pods can talk to all pods, Kubernetes provides network policy API as the means by which you can achieve security for your workloads. These are, how many of you have used network policies or are deploying network policies, right? How many of you agree that this is cumbersome and difficult with regards to, yes. So it's difficult, let's say, right? Because as part of your network policy API, for those of you not familiar, you have a bunch of pods that are the subject of your policy. So these are the pods on which you apply the policy on. And then you define a set of peers, which are other target pods in your cluster. And for both the ingress and egress communication of your pods, you can pretty much define rules that let you control whether you can allow or deny your connections. But network policies work only on layer 3 and layer 4 of the OSI model. There is no way to express layer 2 connections if you want to have, and there's a lot of VM workloads that actually use layer 2 protocols. If you want to express connectivity controls using your MAC addresses, this is not possible using Network Policy API. It always assumes TCP, SCTP, and UDP on layers 4 and 3. So network security from a fundamental segmentation standpoint is missing in Kubernetes, right? You have this one wide cluster-wide network that spans your cluster, and everything is open here. You can add network policies, but you almost always need that network policy controller, the manager, and something that makes sure that the labels are all intact, because network policy works based on label matches. So if your tenant or your user is going to go and change the label, then it stops matching on your pods, right? So namespace selectors, pod selectors, label management, so that's what makes network policies cumbersome. And what I'm going to talk about in my talk is how do you achieve native network segmentation? How do you enable end users to have isolated networks that is tailored to your workloads? Let's also revisit VM networking model. It's pretty basic in almost all the use cases I've heard. And VMs, when you bring them into Kubernetes, there is a CNCF project called KubeVirt, which lets you manage the lifecycles of your VMs. And VMs are basically processes running inside your pods. They're just another container, and KubeVirt helps you wrap it up into a nice box, a gift box, which is in the form of pods. So it has Virt launcher pods that help the VMs run as pods in Kubernetes. Pods are dynamic. They are like cattle. They come and go. You can scale them up and down. This is exactly the power of Kubernetes. But at the same time, for VMs, we need something more stable. Once you bring up a VM, you almost always never want it to be dynamic. You want the IPs to be static. This is like 101 of VM networking for almost everybody I've spoken with. They want their VMs to have static IPs. This is very anti to what the Kubernetes networking model states, which is pods are dynamic, pod IPs are dynamic. There is no way to preserve or persist your pod IPs. And the next thing is the fact that pod IPs are SNATed to your node IPs before leaving the cluster. The traffic is always SNATed. For VMs, there are use cases where people want their VMs to be directly routable within your provider network at least. So you don't want that SNAT to node IP because almost always your VMs have either public IPs or private IPs within your provider infrastructure that should be directly routable with no intervention of the network plugin SNATing things. Live migration, bread and butter of VM networking, during upgrades of your clusters, during node reboots, during maintenance, your VMs will migrate from one node to the other in your cluster. And when this happens, you want the IPs of your VMs to be persistible, to be static. You also want to be able to request static IPs for your VMs. All of these today are not possible with core Kubernetes APIs. And that's actually okay because Kubernetes does not have to solve the problems of all end users, of all niche use cases, right? That's why we have an ecosystem of open source projects here. And we are at the Open Source Summit, so I have to put a slide with all the open source projects that came together to make VM networking possible. Some of these logos you might recognize, the top left one being Kubernetes. The one below it is KubeVirt, which lets you deploy VM workloads on Kubernetes and manages them for you. CNI, Container Network Interface, which is the standard specification that lets you add an interface to your pod, remove an interface to your pod. So this is what all the network plugins like Multis, OVN-Kubernetes, Cilium, Calico, they all follow the CNI standard. This is what helps you networking on your cluster for your workloads, right? Whether it's pods, whether it's VMs, these projects are coming together to make this possible and to fill the gaps that core Kubernetes can't solve or hasn't solved yet. The projects that I'm going to be focusing in on my talk are OVN-Kubernetes and KubeVirt. Both of these are CNCF projects. Starting with OVN-Kubernetes, this is a network plugin that provides robust networking for your Kubernetes clusters. Underneath it, it's using OVN and Open vSwitch. Open vSwitch has been around for a really long time. OpenFlows, it's nothing new. And using these two Linux Foundation projects, OVN and Open vSwitch are Linux Foundation projects. Built on top of these two projects, we have OVN-Kubernetes, which implements enterprise-grade networking for both telco and enterprise customers. So I've put links for the repos and websites on the slides. If you're interested in contributing, please do. And KubeVirt is also an incubation CNCF project. It manages the VM-based workloads for you on Kubernetes, and it's just basically letting you run your containers run your VMs as containers inside pods. So these projects have come together to now come to the crux of my solution for the talk, which is how do you achieve secure native network segmentation for workloads in Kubernetes? We have defined this feature as user-defined networks, which, as the name suggests, any user can come and create a network in the cluster. And then you can have different types of networks tailored to different types of workloads. So there are two new custom resource definitions that you can install on your Kubernetes cluster. A UDN, a user-defined network, is a namespace scoped construct, and you can see sample YAML on my slide as well. This API is mainly for tenants or end users, right? They who are namespace owners or tenant owners, they can simply come, create a network, and then put their workloads in this network. Only the workloads that are part of this network can talk to each other. So if you have workloads in another network, you get the isolation by default. So these are isolated networks that have no contact with other networks. So you can have multiple networks on your same cluster. This is all on the virtual overlay level. And you also have a second version of the CRD, which is specifically for administrators of the cluster, called Cluster User-Defined Network. And this lets admins create a network that can select more than one namespace. So you can couple together 4 or 5 namespaces as part of the same network. You don't need to put any network policies in this case, because if you are part of the same network, you can talk to each other. If you are part of different networks, then you won't be able to talk to each other. Within the same network, if you want more fine-grained control, then you can use network policies, but they are scoped to a network. So we can imagine that today in Kubernetes, we are so used to having this one big overlay network. Instead of this, imagine segmented networks, and all the APIs like services, network policies, gateways, which are namespace scoped, become scoped to a network. So it's kind of like taking one overlay network concept, but into configurable, customizable networks. And the goals with doing this, and it's an opinionated approach, right? You can solve this problem in many ways, and this is how we have decided to solve it, which is using native networking. And so the goals are, firstly, like I said, workload isolation, tenant isolation. This is the primary use case. Being able to segregate or segment your workloads into isolated networks that you can manage and control. This is usually very useful if your workloads are more or less static, like your VMs, which don't really change much in terms of types of applications. The next thing is flexible network topology. So each of these networks that you create can be of different types. They can be a layer 3 overlay. They can be a layer 2, a flat switch on which all your workloads are connected to. Or you can also have another type, which is a local net. And this is mostly for VM workloads. If you want your VM workloads to be directly connected to your provider network, you can do that using local net. Local net is what lets you have an unnatted experience for your workload. So you will have your VMs, public IP, directly leaving your cluster to your provider network. Networks are also of 2 other roles, I would say, primary and secondary. So in case of primary, as the name suggests, it will be the primary network of the pod. So all traffic from your pods by default will be leaving through your primary network. But why should a pod have only one network? Maybe it has more than one interface. Maybe you have multiple interfaces. So you can have more than one network for your pod, which are secondary in nature. So you can always only have one primary user-defined network through which all your traffic leaves by default using the default routes. But if you wanted, I don't know, like an interface towards your storage network, which is separate and isolated from your management network, maybe your workload has more than one interface, then you can have more than one secondary type network. So that's why the role is primary or secondary, and the types are different types. And you can have plug and play, right? You can even come and ask for a specific type of network that we can implement. Overlapping pod IPs. Kubernetes assumes that pod IPs have to be unique, but IPAM address management is pretty difficult. Like you might have cases where you just want isolated networks, but why not reuse the subnets? If they're isolated and if they're not going to talk to each other, might as well have the same subnet there to replicate your workload. So having isolated networks helps you have overlapping pod IPs. So you can actually have more than one pod IP with the same, more than one pod with the same pod IP, but in different networks. All the Kubernetes APIs are supported on all networks. This is the neat bit of it. So any CRs or any core network APIs are supported on every user-defined network. Static IPs for VMs. So in addition to having just isolated networks, this also provides you the ability to request for a specific IP for your VM and for that IP to persist throughout the lifecycle of the VM. There is seamless live migration, which is if you have a network plugin that is giving you a layer 3 type network, it's difficult with live migration because your slicing of the IPAM, usually with a layer 3 network, will be something like you'll get each node of your cluster gets a slice. You might have a /12 or a /16 CIDR for your entire cluster-wide network. But then from there, if it's a layer 3, each node ends up with a /24 or a /23. And in that case, when you live migrate a VM from one node to the other, you're going to have a change of pod IP or at least a break of traffic. So what you really almost always want is a layer 2 network where all VMs are connected to the same flat switch. So that layer 2 type of user-defined network, which is almost all the VM users are using this type of network, lets you have seamless live migration with almost zero downtime. And one of my demos will be around that. Multi-homing, I already mentioned this. A pod can have more than one interface. So a pod can have more than one network. And this lets you custom plug and play things. And access to Kubernetes services. What about DNS and Kube API? We are providing connectivity from all UDNs to Kubernetes API and DNS, so because it's almost always necessary for your workloads to have that connectivity. So we'll see how we do that in a second. So these are some of the main goals behind UDNs and CUDNs. And again, there's several ways to solve it, but these projects have taken this opinionated way of doing it. And here is a sample example. So let's actually dive into a demo to see how this all works together. Imagine you have 4 namespaces, blue, green, yellow, and red, 4 colors, easy to remember. Each of these namespaces can signify a network. So a blue namespace can be having a blue network in itself. So this is a namespace scoped network at the end of the day. So when you have a blue network, you're going to have only blue pods connected to that network, which are part of the same namespace. They won't be able to talk to your green network. So if you try to have a blue pod talk to a green pod, you'll always see that red arrow over there, which means they can't talk to each other. They're in different networks. The red and the yellow are interconnected using a CUDN into the same colored enterprise network. So your red pod can talk to the yellow pod. Let's see how this looks like in a demo. Hopefully the font is big enough for you, for those of you who are at the back. So I just have a very simple kind cluster with 3 nodes, a control plane node and 2 worker nodes. I have the OVN-Kubernetes infrastructure pods that are running as daemon sets. I have the KubeVirt pods also deployed on my cluster. And then I'm creating 4 namespaces here, blue, green, yellow, and red, like I showed in the diagram. And they are all going to have their PUDN, which is the primary user-defined network. So this is a sample YAML that you can see right here. A blue network has the topology type layer 3. So in this case, I'm going to create a shard type network where each node is going to get its own slice. And that's what I mean here by layer 3. It's an overlay network for your pods. And you have a CIDR here, which is 103.103/16. And I'm giving out a /24 to each node on my cluster. It's of a role type primary, right? So these are all the important fields in the CRD. And you have the green networks. I'm creating 2 networks, blue and green, which are of type layer 3. So I'm applying the YAMLs here. And you can see that when you do get this defined network, you see blue and green created. And the blue network will have a status condition that says I'm ready to deploy. And the green network also, we can inspect it, which is what you see here. So if you do the -o YAML for the network, you can see that it's created successfully. Now let's create the CUDN. So in case of CUDN here, you can see I have a namespace selector. The namespace selector is having 2 values, red and yellow, which means I've selected those 2 namespaces to be part of the same network. The topology type is layer 2 here. So this is what I'm going to use for my VM workloads, which means it's one switch. There is no subnetting or giving out a slice to each node. So you don't see a /24 there. It's a /16, which means all nodes are going to get their IPAM from the same range. And I have a IPAM set to lifecycle persistent, which means I want my workloads to have their IPs persistable. So with reboots, with live migrations, I don't want any change here. So I'm also creating the CUDN here for the colored enterprise network, which is connecting red and yellow namespaces. So you can see that it's created. We again do this, OC get YAML for it, and then we can see that the network is created. Now we create the workloads. It's just stateful sets. It's 2 pods per network, so blue, green, yellow, and red. So you can see they're running. One thing to note here, the pod IPs that you see are from the 10.244 subnet. But when I showed you the CRD, it was a 103.103 and a 203.203 subnet. So these are not the UDN IPs. So this is the default network which still exists. And the reason is because Kubernetes itself is not multi-network aware. So KubeVirt, for example, doesn't know about anything about a user-defined network, right? It's something that the ecosystem projects have created. So at the end of the day, I still need that default network for health checks to work. Otherwise, KubeVirt's going to be failing the health check, and then it'll restart your pods. So the default network is intact, but it's only used for health checks. It's an infrastructure locked network through which no traffic can pass except it's used by KubeVirt. So that's why you see the pod IPs here. But this is the real crux of the thing. So in this case, when you see in this snippet, you can see 2 interfaces for the pod, the ETH0 and the UDN1. The UDN1, the 103.103.1.5 is the actual pod IP in this case. That's what's used for all traffic. The 10.244.2.23 is part of your default network, and that is actually not used for anything except KubeVirt health checks. So if you do a -o YAML describe on a blue pod, which is what I'm doing here, that's when you see the details of the UDN network. So Kubernetes itself is not aware about this, but this is how you can get to know what your UDN pod IP is. So if we inspect the Maltese annotations on the pod, which is the CNI and OVN-Kubernetes annotations, this is what you see. So you see 2 interfaces on your pod, one with the UDN IP 103.103.1.5 and the other one with 10.244.2.23, which we don't care about. The interfaces inside the pod look like this. So like I mentioned, 2 interfaces. The routes inside the pod are like this. So you can see that the default route is via 103.103.1.1, which is your UDN network. So that's your default interface. The only reason why the ETH0 exists is to allow Kubernetes and KubeVirt to do health checks. So effectively as part of this, you can see that the infrastructure locked network is your default network, which is useless except for health checks. And then you have the other interfaces here that you see. This is actually described of the blue 0 pod and the blue 1 pod, right? So two pods in your blue network. So if you try to ping within the network, you can see that the ping works. But in this case, it's using the 103.103.2.5 IP of the pod, right? So which is your UDN pod. So within the blue networks, things are working. But if you try to use default pod IP, you can see the ping doesn't work because there is no traffic allowed in that interface. So only KubeVirt can actually ping the pod at that interface. So we do the same, but then for the green pod, so we are inspecting the green pod interfaces, and then we can see that the green pod also has the 203.203.0.5 IP for UDN. Again, the same thing for the green pod. So you can see their interfaces, you can see the routes of the green pod, which is having a different subnet from the blue pod. And you can see that the ping within the green pod also works. If you use the default network IP, it doesn't work. So it's pretty much the same thing. So now you can see the full view of the UDN IPs. So for the blue pods, you have the IPs from 103.103. And for the green, you have it from 203.203. For the red and yellow, we used a 192.168. So the colored enterprise network is isolated from the blue and green networks. So you can see that they're all going to be isolated if you try to do a cross network ping. So if you try to exactly do a ping from blue to green, which is what I see, which is what I'm showing here, you can see that it doesn't work because they are isolated by default. And we have not applied any network policies or anything in this cluster, right? So in this case, the red to yellow works because they are part of the same networks. That's what I'm showing here. And a connection to the Kubernetes API service from all the networks also works. So the DNS and Kubernetes API service are allowed to work. So that's also the last part of the demo. And you can see the egress works. So from blue to, if you try to ping 8888, you can see that the traffic works, but this is natted traffic at the end of the day. If you want unnatted traffic, you have to use local net. So that's like a very simple demo of how the UDN networks work in isolation. And now if we come back to our presentation, but then go to the crux of the presentation, which is VM live migration on layer 2. So I keep talking about this abstract thing of a network, right? I just wanted to put this diagram here on what that means. So this is a view of how it looks like on the OVN layer of what a network looks like. So a colored enterprise network that I showed you with red pods and yellow pods with VMs look like this. And this is what I'm going to do in my demo. I'm going to live migrate a VM, which is having an IP 192.168.0.18 to another node. And we will see that the IP stays persistent. And the internal infrastructure of the network looks like this. It's a bunch of switches and routers. So you have a flat switch, which is spanning all the nodes in your cluster, which is, well, it's having the wrong subnet. It's actually 192.168 subnet that I've used for the demo. And then you can see a gateway router, which is what is used for your egress and ingress traffic from your VMs. So let's look at how this demo plays in real picture. So it's the same thing. I have a kind cluster, and I'm just showing you the describe of the cluster user-defined network that we created before. So you have a layer 2 UDN with persistent IPAM allocation and the subnet 192.168.0.0.16. And you can see that the static IP pods that we created also are pretty much existing here. What we're going to do is to create a red virtual machine. So you can see that I'm using a KubeVirt custom resource, a VM. And we're going to apply 2 VMs here in the colored enterprise network, a red VM and a yellow VM. And these are part of the same network. So you can see that the yellow VM and the red VM is running. So the yellow VM has an IP 192.168.0.18. The red VM has an IP 192.168.0.17. What I'm going to live migrate is the yellow VM, right? So yellow VM and red VM both are on OVN worker nodes. They are in running phase right now, but soon we'll see how to live migrate the yellow VM. But for that, let's try to make sure that the traffic actually works for these VMs. So let's enter the console of the red VM and look at the interface. So unlike inside the pod where you saw a UDN0 interface and an ETH0 interface, in case the VM, when you inspect it, you see only one interface, ETH0. This is actually the UDN0 interface of the pod, right? So KubeVirt itself has bindings for its network to attach the VM interface to the pod interface. And so right now, the ETH0 is your UDN interface inside the pod. And this is having an IP 192.168.0.17. If you inspect the routes, it's also very simple. It's just one link route that you had for that interface. And what we can do next is to try to ping the other VM. So the .18 VM is your yellow VM. So from the red, we ping the yellow, and you can see that it works. We can also try to ping the internet. And you can see that the egress also works. So north, south, and east, west is healthy. And this is how we do on the red VM. Let's also log in into the yellow VM. And what we're going to do on the yellow VM is we're going to start an iPerf server that is listening on port 9000. And we will, so the yellow VM is your server. And in case of the red VM, we're going to go ahead and start an iPerf client. So my red VM is basically sending connections to my yellow VM. Yellow VM is the server, red VM is the client. So you can see that continuous traffic is flowing. What we're going to do here is also have a watch on all the pods on my upper terminal. You can see that there's the Virt launcher pods, red and yellow, that are hosting the VMs. And we're going to migrate the VM. So virtctl migrate yellow VM, right? So I've scheduled the VM to migrate. So this takes some time. And so I might speed up my demo just to the next breakpoint. But essentially, I've migrated the VM. And you can see in a while when the VM successfully migrated in the bottom terminal, right? So my bottom terminal is my yellow VM, which is the server. The terminal above that is red. And so you can see that the bottom terminal will actually terminate right now when I try to finish the live migration. So let's see if we can go to that part. So the console of the yellow VM will basically crash when the migration finishes. And you can see that, right? You can see that the VM actually quit. And at the same time, you can see that there's a slight variation in the packet size. It went from 3.14 megabytes to 2.3. So you can see a slight drop in the yellow VM. But when we log back into the, if we log back into the yellow VM, the new VM, which is basically, because the old one was basically turned off when we migrated, because the yellow VM is now on the new node, right? So you can see here in the tab above that the virt launcher yellow has 2 pods, one in completed state, which was in the old node, and then you have the new VM in running state on the OVN control plane node, which is where it launched newly. But you can see if you log in back to the console, the traffic is not broken. So even on the yellow VM, you can pretty much see that the traffic is intact. So the red to yellow traffic doesn't break, though there is a dip, right, in the traffic. So it's because they're on the same layer 2 network. And the neat thing here to also check is the IP of the VM. Oops, I didn't. So the IP of the yellow VM in the bottom terminal here, you can see it stays as 192.168.0.18. So even after it live migrated, the IP of the VM doesn't change. So that's basically what I wanted to show you, that static IPs, persistent IPs, seamless live migration, all of these are possible using user-defined networks. So going back to our presentation and continuing here, if I can get it back to full screen. There is also another part that I want to talk about before I end the talk and open it up for questions, which is I also mentioned that VMs can be having IPs that are directly routable from external clients. So there is a new feature in OVN-Kubernetes, which is route advertisements, which allows you to now take this one step further. How can you advertise your user-defined networks, your UDNs, to external clients outside the cluster? We are leveraging open source projects, FRR, which everybody knows in the community, and FRR Kubernetes, which is the Kubernetes version of deploying FRR as a BGP speaker or daemon set on every node in your cluster. Using these 2 open source projects and leveraging OVN-Kubernetes implementation of this, you can basically select what networks you want to advertise to outside, right, using BGP. And using this mechanism, you can import routes from outside clients into your cluster. You can export routes, you can import subnets and export subnets. So you can export your pod CIDR subnets to outside. So you can choose which networks you want to advertise. And you can see a route advertisement YAML sample on my slide where you have the network selectors, and I've selected any network with the BGP network label on it. I want to advertise it. So when you do this, if we go back to our example of a blue network and a colored enterprise network, and I'm advertising a blue network in my case, which had the subnet 103.103.0.0.16, using the route advertisement YAML, I can advertise the subnet from each of my cluster to your provider edge router and to your provider network. So all your pods become directly routable. And this is pretty cool because this also lets you have another way of customizing your networks to the point where you don't even need an overlay anymore. You can basically just use BGP as a way to have your pods talk to each other. So this lets you also have more throughput because you don't have encapsulation or the Geneve tunnel or anything that is required in the middle. And it also provides more extensibility to end users. There's also features on the roadmap like EVPN, which lets you extend every one of your networks inside the cluster to your provider network. So you can have your blue network, which needs to extend via BGP VPN or through VRF light isolation mechanisms to your finance network, for example, or you want your colored enterprise network to be your HR network, which is in your provider network. So all of these plug and play mechanisms are made possible, and that's the direct ingress to your VMs using BGP. So before I open it up to questions, just takeaways and a summary of everything I covered in my talk. It's possible to do network segmentation, native network segmentation on Kubernetes clusters. It's also possible to create user-defined networks and cluster user-defined networks. According to your own workload's needs, you can segregate your applications into isolated networks, and that's as simple as it, like I showed you in the demo. It's possible to request for static IPs for your VMs. It's possible to persist them across reboots and maintenance and upgrades. And that combination of all of this is what lets the users have the power to configure their networks. I think this is the really crux of my presentation and the takeaway. With Kubernetes, the networking was always almost static with one cluster-wide network and depending on your end user, whether you're a telco customer, whether you're a virtualization customer, whether you're an enterprise customer or end users, it was hard to get what you wanted out of it. And this is what OVN-Kubernetes is bringing to the table, to the community. We are an add-on network plugin on top of Kubernetes that lets you plug and play and customize your networks. And we also want to hear from all of you. So if you have use cases, please open issues on GitHub. And we are more than happy to have several types of networks that we can accommodate, because it's, at the end of the day, plug and play for end users. So thank you very much. I'm opening up door for questions. Yes.
There is also an initiative in Kubernetes on the multi-networking. How does it actually relate to that?
Yeah, that's a great question. So SIG network, multi-network is a working group which is also trying to aim to solve this exact same problem. It's been several years now. It's been 5-6 years. And one of the things that community tried to do in the beginning was to introduce a concept of a pod network. They tried to directly edit the spec of the pod, which was a big no in the community, because everything in core Kubernetes is almost always not changeable. So then there was a setback there, and now they're trying to do an out-of-tree network spec. And again, the challenges there are the balance in defining the API. So what's happening is they're trying to do something very similar to UDN, which is coming up with a multi-network spec. But what do you put in the specification? Because when you are a part of the Kubernetes SIGs working group, you have to keep it generic enough and let each network plugin be able to customize it. But then when you put it that way, the spec becomes like a network attachment definition, which is not specific. So an API needs to be well written, but if you're not able to find consensus in the community on what are the different fields, right? Like I mentioned, I used the word opinionated for a good reason. A layer 3 or a layer 2 or a role type primary, all of these are very specific to my plugin, which is OVN-Kubernetes. Someone like Cilium or Calico might have different ways of doing it. So when you represent all those use cases as a generic API, it's becoming very hard to find consensus and balance between leaving that room for creativity on the network layer, but at the same time having something of a standard that everybody can use so that everybody's not doing their own thing. So I think there were some challenges, and they're still trying to figure it out. But our goal is to make sure that the use cases we are presenting here is also represented that. So we do have members who go to those meetings and make sure that it's represented. So it's very much related. And at some point, we want to see that standardized across Kubernetes to be able to deploy those multi-interfaces, multi-networking, and for Kubernetes itself to be aware of multiple networks, but we're just not there yet. And yes, yeah. So we're also trying to make sure that it's expandable, and even if there is a new API that comes up, we'll make sure it's backwards compatible, and we have both. Yeah, a great question. Thank you. Yes. Yeah, most of the use cases that I've seen is legacy systems and very old applications and some of them actually even have like Java applications with specific IP that they're tied to in the code. So it's really legacy. Then they bring it into, and most of them are not ready to be containerized, if I have to provide my honest opinion. But given the hype and the move to Kubernetes and containerizing and bringing all your workloads to the cloud, it's become hard for the VMs to be just gift wrapped, and so that nothing much changes, and you can just bring them in. But yeah, mostly that's how I would define it. That's also. Yeah. That's actually a great question also. So BGP in itself, one of the main pain points there is it's tied to the infrastructure at the end of the day, like your provider router, where you're sitting and how you're integrating it. If it's AWS, are you using a transit gateway router? Even during testing and quality verification of the feature, we are hitting the same bottlenecks. The way we define and run it on-premise for bare metal is not the same as when you deploy it on clouds, because each of those clouds might have different integration mechanisms. So at the end of the day, what we tell is as soon as you are leaving the node in some sense, then the troubleshooting kind of falls upon the provider stack on how you are having your tool set up for that part. Like, so we are saying that as long as it's within the OVN-Kubernetes and the FRR-Kubernetes realm of things, and we are making sure that we'll have you troubleshooting stack to make sure the routes are imported correctly, the VRF is plugged in correctly, all of that. But as soon as it's leaving your node, then it becomes like a shared domain problem with the infrastructure also. So it's a great question. It's one of the pain points that we're also having with regards to integration across platforms. So I think you have, yeah.
Is there also support for other routing protocols like OSPF, for example?
Yeah, we are open to actually doing that. We've not had strong push from the community for that, but if there are use cases, we would love to, add more protocols. And we are not tying it to anything specific. So we are trying to also keep it a little bit open, the API, saying we're advertising it, and then we can also, and there are enhancements also up and running where we're trying to think, maybe there will be future protocols that people would love to see there. So if you have use cases, please, comment on. Yes.
Does OVN coexist with Calico?
No, OVN does not coexist with Calico, though I have seen people trying to get half nodes on Calico and half nodes on OVN. It's not well tested, but it is possible to have half and half. It's just a pain, I would say. Yes, you have to essentially pick the network plugin. I think this is also one of those pitfalls in terms of CNI. Yes, it's a good standard, but we didn't standardize on implementation. So for good reasons, because every network plugin like Calico specializes their own thing, OVN specializes their own thing. So at the end of the day, mix and match never goes well. Like, it becomes hard over time. Like, you might get it successful and running in the first go with some nodes on Calico and some on OVN, but you'll have to continuously keep testing it with every release, and that keeps a problem. So most of them I've seen end up shifting towards a monolithic architecture. Yes.
Yeah, I work with a lot of telco customers, and one of the use cases basically about data acceleration, like using OVS with DK. Today, KubeVirt doesn't support that. And the follow-up question with the Calico is that you can't use OVN-Kubernetes with Calico. So if I have to use OVS, then I have to switch the whole CNI stack from Cilium to OVN-Kubernetes. So is there any plans to support the OVS with KubeVirt actually? The existing CNI uses like Cilium or Calico. You can use KubeVirt and provide OVS.
So the acceleration is supported with KubeVirt, with VMs, with OVS on OVN-Kubernetes. We actually have upstream community. In fact, NVIDIA contributes also to OVN-Kubernetes, and they are actually running VMs with acceleration on OVN-Kubernetes. So maybe if you reach out on our CNCF Slack channel, I can try to provide more details. One of the things that we lack is documentation. So a lot of things we support is not exactly there. I admit this as a maintainer, and I'm trying to fix it. But this is something we support. So I would love to see if there's something specific that didn't work, but we can take it offline on the Slack, yeah. 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 Yeah, both of them great questions. For the first one, whether Calico supports it with OVS, I guess we'll have to go to Calico to ask if they want to do that. The second one for VPP, and if we have plans to replace it, we went with FRR Kubernetes and because MetalLB is also using FRR Kubernetes at the end of the day. So it was easier for us to integrate with CNCF projects that existed already. So both FRR Kubernetes is also CNCF, and so the integration was more seamless. It was out of the box. It's not that we can't, but we would need a strong justification on why that is better than what we have, and if there is like pros and cons in how BGP is implemented on the router level for FRR. Yeah.
One last question, I promise. So if you did a line migration here, I have seen that the IP is preserved, but the MAC address is not preserved. So if you have some firewalls based on MAC address filtering, how does this line migration work?
Yeah, so we are actually also having a feature for requesting static MAC addresses as well that is preservable. So I'm not sure if I showed that in the demo. Did the MAC change? I didn't notice if it did. Yeah, I need to check. But it is possible also to preserve MAC addresses. We are trying to have both static IPs and static MAC requestable and also preserved with live migration reboots, because the MAC, I think it shouldn't have changed because the MAC is derived from the IP in OVN-Kubernetes. So the algorithm is such that if you have 192.168.0.18, MAC's always the same. Like the 6-byte address we derive from the V4, it doesn't change. I'm pretty sure it's preserved, yeah. Yeah, but in this case it doesn't. I'm pretty sure I preserved the MAC, and that's because OVN-Kubernetes is in charge of the static IPAM in this case. We always pick the MAC from the IP. So if your IP hasn't changed, it means MAC changed. And you can also request for specific MAC in our latest release. So on the VMs, so these things never change. But great question again. Yes, I think that's the last question because we're at time. I didn't hear that, sorry. The roadmap? Are you saying what's on the roadmap? Is it already supported or? Route maps. Yeah. I would need to think about that. So what you're saying is route maps on the VM level or on the VRF level or? Yeah. Oh, yeah. So no, not today, unfortunately, but we do have that also as part of the additional feature requests because a lot of them are asking for being able to configure this in a way they want. So yeah, we'll get to it soon, I think.
Can I ask one? So what are the limitations with FRR in Kubernetes then in this case?
To the best of my, I don't directly work on FRR Kubernetes, so I will admit my knowledge is limited. We do have some bugs around the way the FRR configuration itself is set up and deployed. So today it's not exactly mutable. So if you want to add or remove your routers in your specific autonomous systems places, it's kind of like a recreate of the FRR config in the way we are reconciling things. So that's one of the bottlenecks that we've seen, but we've also got requests to try to change it. So we're trying to see how to go about it well. And otherwise, it's been, we're waiting to hear more feedback, but so far it's been, this is exactly what we want, and thanks for doing this kind of feedback we're getting. So, yeah.
Kind of blew my mind with FRR integration.
Yeah, and one other challenge we have is also that today we don't let you select what nodes you want as BGP speakers. So FRR is on every node. This is not scalable, so we're trying to see how to have node selectors as a way to have segregation of routes. And on layer 2, because it's an advertisement of /16, it's possible that every node advertises this. That also won't scale. So we're trying to see how to have a slice without having an actual slice so that every node is advertising a part of it. So route aggregation optimizations. There's a lot on the roadmap in that sense, but yeah. Thank you. Yes. Thank you everybody for joining. We are at time. Really appreciate it.